All right, let's jump right into this explainer. Today, we're going to be breaking down the fundamental building blocks of our planet, and we're doing it by looking strictly at some absolutely fascinating lecture notes covering primary and secondary minerals. We're going to see what Earth is actually made of, straight from the source.
Here is our roadmap for today. We'll hit 1. Defining Earth's minerals. 2. Dominance in the crust. 3. Classification of minerals. 4. The primary silicates. And 5. Mineral weatherability stages. Starting right off with Section 1, Defining Earth's minerals. So, what actually makes a mineral, well, a mineral? It's not just any old rock. To fit the definition, it's got to be a naturally occurring, homogeneous element or an inorganic compound. Plus, it has to have a definite chemical composition, and it absolutely must possess a characteristic geometric form. It literally requires all of those specific traits. And what's really wild is the sheer scale of this when molten magma solidifies. As that magma cools down, the different elements present just freely arrange themselves, guided by attractive forces and those geometric forms we just talked about. The result? Over 2,000 known minerals are formed. 2,000.
Moving right along to Section 2, Dominance in the crust. Now, with over 2,000 options, you'd probably expect a really diverse mix in the crust, right? Well, not exactly. Feldspars absolutely dominate here, making up a staggering 61%. After that, we've got ferromagnesians at 16.8%, quartz at 11.6%, and secondary clay minerals at 6%. Everything else combined is just 4.6%. In fact, if you look at the big picture, silicate minerals take up a whopping 90% of the rock composition in the Earth's crust.
Which leads us to an incredibly important structural point. Since silicates make up 90% of the crust, understanding them means you have to understand the silica tetrahedron. The silica tetrahedron is the fundamental building block of all the silicate minerals of the Earth's crust. It is the absolute key to that massive dominance we just saw. All right, let's look at Section 3, Classification of Minerals. Let's talk about how geologists actually organize this massive array of materials, starting with classification based on quantity. We have essential minerals versus accessory minerals. Essential minerals are basically the VIPs. They form the chief constituents of a rock and actually determine that rock's character. Quartz, feldspars, and micas fall right into this category. Contrast that with accessory minerals like tourmaline, pyrite, or magnetite. These show up in really small quantities, and their presence or absence has absolutely no consequence on the character of the rock. They're just kind of along for the ride.
We can also categorize them by specific gravity. Light minerals are abundantly present in nature and have a specific gravity below 2.85. This group includes our dominant heavy hitters, quartz and feldspar. On the flip side, heavy minerals have a specific gravity above 2.85. Examples there include hematite, pyrite, and olivine.
Which brings us to Section 4, the primary silicates.
Let's dive into how the physical linkage of those tetrahedra we talked about completely dictates the mineral group. Think of it like a mental filing cabinet. If the linkage is an unlinked island, you get orthosilicates, like olivine. If they form a single or double chain, you get inosilicates, like pyroxenes and amphiboles. A layered linkage gives us phyllosilicates, like the micas, biotite, and muscovite. And finally, if they link up into a complete framework, we get tectosilicates, which include quartz and feldspars.
Let's put the spotlight on those tectosilicates for a second, because these are the true heavyweights of the crust. Quartz has a framework that is insanely densely packed and highly pure. Because it's so tight and electrically neutral, it completely prevents substitution, making it highly resistant to weathering. Feldspars, on the other hand, have a less dense framework. They're the most abundant rock-forming minerals, and they serve as a really vital storehouse for sodium, calcium, and potassium in soils. But hey, it isn't just structural density that matters here. Chemical composition radically changes how vulnerable a mineral is to the elements. Let's compare two of those layered phyllosilicates, the micas. Muscovite, or white mica, is non-ferromagnesian, found in acid igneous rocks, and is notably resistant to weathering. Now contrast that with biotite, or black mica. Because biotite is ferromagnesian, meaning it contains iron and magnesium, it's actually highly susceptible to weathering. So this stark contrast between muscovite and biotite really brings up a crucial question. Out there in nature, under the constant, brutal assault of the environment, which minerals actually survive the ultimate test of physical and chemical weathering. And that leads us to our final part, Section 5, Mineral Weatherability Stages. This is essentially a dramatic multi-step survival story. Step 1 is the early stage of weathering. This is where those ferromagnesians like olivine, pyroxenes, and amphiboles break down pretty easily. Then we hit Step 2, the intermediate stage of weathering. Here, more robust minerals like orthoclase, muscovite, and our densely packed quartz hold out much longer. But eventually, we reach Step 3, advanced stage weathering, which just results in complete breakdown. In fact, the source material leaves us with this very definitive final rule. Highly weathered soils do not contain any primary minerals. So, while you're definitely going to find primary minerals in young soils, once they reach that advanced stage of weathering, they're completely wiped out, fully replaced by secondary minerals. So keeping all of these incredible processes in mind, from magma cooling into intricate geometrical forms to the sheer dominance of silica frameworks and the brutal stages of weathering, I want to leave you with this thought. The next time you step outside and examine the dirt beneath your feet, are you looking at the beginning of a primary mineral's life or the very end?